If we have a charged particle moving to the right through an external magnetic field that's, let's say, pointing into the page as represented by this X, then that charged particle will experience a magnetic force. Can you tell me which direction that magnetic force will be on this negatively charged particle? It's going to be downwards, right? It's going to be the hand rule for deflection, left hand rule for deflection, thumb, fingers, palm points downwards. Good. It's going to want to follow a circular path as it goes through that magnetic field. Let's say I have another one now. We're not getting rid of that charged particle. We've got another negatively charged particle that's going to the right. It would also experience a force downward, right? Say we've got another one, a third one. It also experiences a force downward. A fourth one also experiences a force downward. If all four of these negatively charged particles are exposed to this external field, they will all experience a force initially downward, and they will all travel in a circular path. Unless these four negatively charged particles are encased, unless they're inside a piece of copper or some other conductor. If these charged particles are inside this piece of copper, in other words, a wire, then they'll all still experience a force downward. Thumb, fingers, palm still points downward, but they can't go in a circle anymore. They can't go in a circle because the wire physically prevents them from going in a circle. These electrons all experience a force downward, and instead of going in a circular path, they're going to end up pulling the wire downward with it. So now we say that there's a force on individual electrons moving through a magnetic field, but if there's an electric current in a wire, which is really just a bunch of moving electrons in the wire, then the wire itself will also experience a force in the same direction as the negative charges. How do we find the direction of that force? We're going to use the hand rule for deflection. If you figure out what the force is on an individual negative particle, it's the force on the wire itself. How do we figure out what the magnitude of that force is? Well, we introduced that last Friday when we talked about the lab. The force that acts on this wire is going to be equal to I times L times B. What's F stand for? The magnetic force, right? And it's going to be measured in newtons. What does I stand for? Patrick? I stands for the amps, or the electric current. The current is the rate of flow of charge. We talked about this yesterday. Remember, we introduced an equation for it. If you don't know what I is, then let's find I using Q over T, the rate of flow of charge. How many electrons or how many coulombs are flowing per second? What does L stand for? Somebody else? What does L stand for? The length of the wire? Be careful with that. You're correct. But last Friday when we talked about this in the context of the lab, we didn't specify exactly what length of wire we mean. You've got an entire roll of wire, only part of it's exposed to the magnetic field. You're only going to use the part that's exposed to the magnetic field. In addition, you're only going to use the part that is perpendicular to the magnetic field. So we're going to say here for L, it's the length of wire exposed to the external magnetic field and perpendicular to the external magnetic field. For instance, let's say we've got two magnets here, a north pole and a south pole. That north pole and the south pole here creates an external magnetic field that looks something like this in between those two magnetic poles. Let's say we've got a wire that goes like this. Okay, the electric current goes up like this, and then over like this, and then down like this, and then down below it's connected to a light bulb or a motor or something. It doesn't matter. Let's say this first length of wire is 5 centimeters. The second one is 8 centimeters. And the third one is 5 centimeters again. What L would we use right there? We'd use 10. Good. We use the length of the wire that is, first of all, in the external magnetic field. And second of all, the length of the wire that's perpendicular to the magnetic field. The reason we don't use that 8 centimeter length of wire, we don't care how long that is. The reason we don't use that is because those electrons that are traveling through that wire are traveling parallel to the field. And when electrons are traveling parallel to the field, the force acting on those electrons is 0. We only want the part of the wire that's in the field and perpendicular to the field. And we want to measure that in meters, always. Measure it in meters. Finally, B, the last one, we've kind of already said that. This is the external magnetic field. It's the one that's caused by those two magnets, the North Pole and the South Pole, or caused by an electromagnet or whatever. Is that okay? If you've written down what I just wrote down on the previous page, then you don't really need to copy this because you basically already got it. If you haven't, then maybe write this down. Remember what I means, remember what L means, and remember what B means. And remember, when you multiply those together, assuming L and B are perpendicular to each other, then you're going to get a certain force measured in newtons. Let's do an example now. 12.4, page 605. An 8.5 centimeter long conducting wire. Remember, I circled the centimeters. Okay, the mistake that I made on the quiz that I gave you today was not circling and identifying those things that could cause me to make a silly mistake. It wasn't unit conversions like we have in this one. It was what type of particle we had, so I forgot which hand rule to use. Okay, but it illustrates a good point, and that is make sure you highlight or underline or circle or something things that can cause you to make a silly mistake, like unit conversions. 8.5 centimeter length of wire lies perpendicular. That's important because that allows us to use the equation we just learned. To a magnetic field of magnitude 4.2 millitesla. Again, strange units that we got to end up converting here before we use them. If there's a negative charge flow just means that it's electrons that's moving here. We call it electron current, another term for it, electron current. If you ever see the term conventional current, then it means the flow of positive charges, which doesn't really happen within a wire. But every once in a while, we still see that term, conventional current. Okay, if you ever see that conventional current, the math of it works exactly the same as it does with electron current. But instead of using the left-hand rule, you'd use the right-hand rule for deflection. Conventional current, right hand. Negative current, left hand. We want to find the magnitude and the direction of the magnetic force on the wire. So this is going to be our length. This is the part of the wire that's perpendicular and exposed to the magnetic field. This is going to be the magnetic field value. This is going to be the current, 2.10 amps, and we're looking for the value of the magnetic force. The equation that we're going to use is the one that we just learned. There's no problem with using that because the particles are moving perpendicular to the field. The current here is 2.10 amps. The length of the wire, we got to convert to meters. It's 0.0850 meters. I noticed a number of people between period 2 and period 3 on their labs used a length of wire of 8.4 centimeters. When they converted that, they converted it as 0.0084 meters, not 0.84 meters. We're dividing by 100, not by 1,000. So 8.5 centimeters becomes 0.085 meters. The magnetic field is 4.2 millitesla, and that's going to be 4.2 times 10 to the minus 3 Tesla. We do that, we get 7.5 times 10 to the minus 7. Was it? I think it's 10 to the minus 4. What did you say, Bryson? Just try typing it in again, make sure you can get the right answer. 10 to the minus 4 rings a bell, actually, from this morning. 7.5 times 10 to the minus 4 newtons. That's the magnitude of my force. Now, I can find the direction of the force by the hand rule for deflection, same as I did if it was an individual charged particle moving through this field. We're talking about negatives. Okay, negatives are leaving the negative end of the battery going around clockwise here. Let's stick our thumb into the page. That's what they mean this to be, is into the page. Okay, they try to draw it in 3 dimensions. Sometimes that confuses people. But in the end, that's still what they're trying to represent here. Particles going into the page. Fingers in the direction of the field from north to south. Palm's going to point upwards. So the magnetic force is 7.5 times 10 to the minus 4, and it's toward the top of the page. Okay. Okay, yeah, that'll do it. It's a pretty straightforward question. The equation is easy, as long as you do your unit conversions. The hand rule is, I wouldn't say it's easy, but it's no harder than it was this time last week when we were finding the force on individual charged particles. It's exactly the same thing. Try these two questions, see what you can do with them. Now let's take a look at the second question here, everyone. It says a thin conducting wire 0.75 meters long has a mass of 0.06 kilograms. What's the minimum current required to make the wire float in a magnetic field of 0.515 Tesla? We've got a few variables here, nothing to do with the unit conversion, so that's good news. This is going to be the length of the wire. This is going to be the mass. This is going to be the magnetic field strength. We're looking for the current required to make it float. This is a big word right here, float. We've used words like that before, but I don't think we've used that exact word in any of the problems we've done so far. Float, suspend, hover, maintains its same position above the earth, or maybe it's parallel, remains parallel to the earth. All of those things mean the same thing. All of those things mean that the forces have to balance. There's a force upward that balances the force downward. What two forces are balancing each other in this question? Gravity, somebody said, is one. And what's the other force? Gravity and the magnetic force. Good. So it's Fm equals Fg. Now, we've done these problems with charged particles maintaining the same position above the Earth. The magnetic force in that case is QBB. Here, the magnetic force is ILB. But it still becomes magnetic force equals the gravitational force. We're going to solve for the current here. It becomes mg over L times B. I don't like this word minimum current. That's not right. That's not correct. It should say what is the current required to make it float. Because if you're below that current, it's not going to float, it's going to fall. If you're above that current, it's not going to float. It's going to, the magnetic force is going to be bigger and it's going to rise. So if you want to make it float, hover, maintain the same position, then you don't want to have a minimum current. You want to have an exact current. And that's the exact current we're going to need, 5.2 amps. Good? Okay, what I'd like you to do right now, please, is take a look at worksheet number 13. There's 5 questions on that. I'll give you about 10 minutes to see what you can do with that, and then if there's anything we need to go over after that 10-minute period, we'll do that. And then we'll move on to a tiny little bit of new stuff beyond what we've already done here. All right, we've got the answers to worksheet number 13 up on the board now. Take a look, see if you have any questions about any of those 5 questions. Any issues? No? All right, if you haven't quite finished the worksheet, that's okay. Just write down these answers so that you can take a peek at them tonight after you've done the questions, and then just pop in during scheduled help or something tomorrow and ask me. I say that because we're going to have a quiz tomorrow on this stuff. So I'm assuming, yes, on this stuff, yeah. So I'm assuming that you're going to be good with this. Okay, I'm assuming that you're good with this now if you're not asking me any questions on it now. If you do happen to find a problem tonight, pop in 11:30 tomorrow morning and I'll help you out with it before we have our quiz, okay? I want to take a quick look at an application of this magnetic force on a wire here right now. We try to, every once in a while, provide you with an application or two of what we're doing so that you can see that it's not just some kind of theoretical thing. You know, why? Oh, yes, a wire experiences a magnetic force when it's in a magnetic field. Who cares? Okay, there's applications to all of this. And we try to provide you with some of those applications. This is an electric motor. It's the basic device that's going to be present inside a number of things, including your electric toothbrush, an electric drill. It's going to be the basis in the electric motor part of a hybrid car or of just a straight electric car. It's going to be the basis of anything, basically, that spins as a result of electricity. A fan, you flip on the fan in the summertime to cool you down. Ceiling fan, okay, on your ceiling in your house. All of those are based on the exact same principle that we're going to talk about over the next few minutes here. There's a few parts to this electric motor, a few basic parts, and only a few basic parts to the motor here. You see the little electric circuit here in the bottom left-hand corner. That electric circuit has a battery in it, and of course that battery has a positive end and a negative end. The electric current leaves the negative end and goes around clockwise here. That electric current touches or goes through this little black thing here that we call a brush. This brush is in contact with, but isn't touching this thing that we call a commutator. So this commutator is allowed to move while maintaining contact with the brush, but not actually connected to the brush, if that makes sense. So the electric current is going to go through this brush, it's going to go through this commutator, and then it's going to go through this wire around here that we call the armature. The armature is what actually spins. After the electric current has gone through the armature, it goes back through the commutator, through the other side of it, back through the brush, and then back around the circuit clockwise, back to the battery. Well, how does this thing spin then? How does this armature spin around? You can see that if we have an electric current, Bryson, an electric current that is going up this way through the magnetic field that goes from north to south, you can see that that wire and therefore that current is perpendicular to the magnetic field. It experiences a magnetic force. We could figure out the direction of that force, say thumb, fingers, palm. The direction of the force on this wire is going to be upward. So it's going to be pushed up. If we go around to the other side, the direction of the magnetic force would be downwards. So it's going to be pushed down. What happens is, if this represents my armature right here, okay, one side, the other side, this side's pushed up, this side's pushed down, it ends up rotating. We get what's called torque. We get torque on this, and it rotates. But it only rotates 1/4 of a revolution before the commutator, before this little gap in the commutator right here, this little insulating gap right here, is in contact with the brush. Now the current stops. So take a look at this piece of paper up here again that's representing my armature. It spins around 1/4 of a revolution because of the magnetic force. Then the current stops. So there now is no magnetic force. But it keeps spinning a little bit just because of inertia. You know, things want to keep moving. So it keeps spinning a little bit because of inertia. Once it spins past that 1/4 of a revolution, then the current starts going again. But the current's going to go this way. Then it's going to go 1/4 of a revolution, and so on and so on and so on. The current reverses through the wire, but yet it still goes clockwise. The current's reversing through the wire because we'll call this wire A, or side A and side B. Side A, when side A is rotated to the point when it's over here, where side B was, and side B is now where side A is, the current's going to go around it's going to go around clockwise still, but it's not going to go from A to B. Once it's made that 1/2 of a revolution, and B is over there and A is over there, the current's still going to go clockwise, but it's going to go around from B to A. So the current is reversed in terms of the direction it's going through the wire, but the overall direction of clockwise is going to be the same. That keeps the magnetic force in the same direction on each side of the wire at all times. The magnetic force on the left side of the wire will always be upwards, and the magnetic force on the right side of the wire will always be downwards. You always have that torque that causes it to rotate in this direction. So it spins. Okay, the magnetic force stops, but it keeps spinning because of inertia. Then the magnetic force starts acting again, spins again, again. The cycle keeps repeating itself over and over and over again. So ultimately, this armature keeps spinning around as a result of this magnetic force and its inertia. Now, so what? Something's going to be connected to this armature. Maybe it's a drill bit that's connected to the armature, and you drill a hole in a piece of wood. Maybe it's the brush on your toothbrush that's connected to this armature, and it spins around. Maybe it's the fan blades of the electric fan that's on your ceiling that's connected to the armature, and it spins around. Maybe it's the axle of an electric car that's connected to the armature, and it spins around. Now, you got a drill. You guys have all used a power drill at some point, probably. You've probably never driven an electric car, but you know that if you would drive an electric car, you've got to be able to control the speed of this motor. How do you think we could control the speed of this motor? How do you think we could make this motor spin faster or slower? Give me one way. Good. Control the current. If we increase the current, if we increase the amount of current that goes through the circuit, then the magnetic force will increase. If it's a stronger force, then of course it's going to rotate faster. What else could cause the force to be bigger besides a bigger current? Dan? Good. The length of wire that's exposed to the magnetic field. Now, how do you make the wire longer? How do you get more wire exposed to the field? It's actually pretty easy. Take this loop of wire. When you come around here, don't have it connected to the commutator. Keep going around. Now maybe you've got it connected to the commutator. Now you've got 3 times the amount of wire that's exposed to the magnetic field, and therefore you're going to have 3 times the amount of force that's acting on this wire. Now, careful with that. This is the only part of the wire that I care about. Why is this wire irrelevant? Because it's parallel to the magnetic field. What else could I do to cause this thing to spin faster? You pull the trigger of the drill. You want the drill bit to spin faster, to drill a hole through this tough wood. Stronger magnetic field. To have a stronger magnetic field, all you're going to do is have stronger permanent magnets right here. When you pull the trigger on that drill, what are you doing? You're not changing the length of the wire. You're not changing the magnetic field strength. You're changing the current. Okay, when you pull the trigger, you're allowing more current to flow through the motor, which gives you a stronger magnetic force, which allows it to spin faster. Yep? I'm not sure what you mean. What's the shape though? You're okay. No, I don't think so. If you magnetize it, it would still have a north pole and a south pole, but I don't think it would be an inside-outside thing. All right, guys, that's it for today. No homework except tomorrow we have our little quiz. Make sure you come see me during schedule to help you if you have any trouble. Don't forget your test on Monday as well, unit test on Monday as well.